So now that we've defined what a function is, let's start working with some functions. This is function notation. You've seen it before. F of x is just a way of saying y equals, only using function notation, which is much more convenient as you begin to process functions, which we will do a fair amount of today. So we want to find the f of 3. That means for this function, what do we get, or what's the value of this function if we plug in at 3 for every x? Now, I'm going to show you something right now that'll seem like much ado about nothing, and there's a good reason for it. You'll see it very soon. But it's called the big gaping hole method or algorithm. When you want to plug or find this value, this function value at 3, I think it's easier if you put parentheses just around the variable. So you just carve parentheses around the variable in the function and then rewrite the function without the parenthesis, or without the variable inside the parentheses. So you're sort of creating a parking space for the value that you want to plug in. So this is the big gaping hole algorithm. I'm going to set it up here. I have a parenthesis, squared minus 2, open paren, close paren, minus 8. And so what I've done is I've created a space where I can now plug in that 3 to replace the x. And then simplify from there. 3 squared is 9, minus 2 times 3 is 6, minus 8. So 9, take away 3, minus 5. Okay, now I know what you're saying is, Marla, what on earth are you telling me to do? That's crazy. Who would make that mistake? But on the very next example, you begin to see how it can be easy to confuse your values, especially with negatives, and how having a method to not get lost in what you've done or in your work while you're working is useful. So in this case, negative 3D, already we're starting to look a lot more complicated than we were just a minute ago. So open big gaping hole, squared, minus 2 times big gaping hole, minus 8. Now I'm going to put in my negative 3D, and you can sort of see that this is the place right here where a lot of us make a mistake when we're trying to make substitutions and we're working with negatives and our brain is trying to go ahead and make some alterations to it. And even here, sometimes we'll make mistakes in this case. So at this point, there's no mistake to be made because negative 1 squared is a positive 1, 3 squared is a 9, and d squared is d squared. Minus 2 times negative 3 becomes a positive 6d minus 8. And I've ended up with another parabola, and there's nothing I can do with it at that point. Okay, so that was slightly more difficult. Probably could have gotten there relatively easily and probably mostly correct. But what about a case that looks like this? F of x, or the f of 2a minus 1. This would be really easy to confuse. So I'm going to do big gaping hole again, minus 2 times big gaping hole, minus 8. And watch this. 2a minus 1, 2a minus 1. All right, so the first one is the square of binomials. So that's 4a squared minus 4a plus 1 minus 4a plus 2 minus 8. So 4a squared minus 8a plus, minus 4 plus 2 is negative 2 minus 8. What did I do here? 8a. Oh, 1 plus 2 is 3. Take away 8 is a negative 5. There it is. All right, so this can get pretty complicated, and trust me, this isn't as complicated as it can get. So when it's a simple problem, I would say just go ahead and make your substitutions. But whenever what you're being asked to substitute is more complicated, just set yourself up to succeed. Make a big gaping hole and then go from there. All right. So now that we're working with functions, we have to be able to define the domain of a function because we don't want to be choosing x values that aren't allowed. If we have a restricted domain, we can't even try to choose the input value on the restriction. So let's look at determining the value of a couple of domains. So find the domain. All right, so we want to find the domain of g of x equals the square root of 4x minus 1. So let's think about square roots. What do we know is not allowed to happen to a square root? Well, you're not allowed to have a negative number inside unless you're on the imaginary plane, and we're not. We're dealing with functions in the real numbers. We don't have we haven't moved into the imaginary plane. So we need to make sure that the values created by 4x minus 1 are equal to or greater than 0. So we want to say, this is a big fatty semicolon, which to me says, Mayday, Mayday, you got to pay attention here. 4x minus 1, these values have to be greater than or equal to 0 because you're allowed to have a square root of 0. But you're not allowed to have a square root just less than 0. And so now we'll just go ahead and solve. 4x has to be bigger than or equal to 1, just adding 1 to both sides. So x has to be bigger than or equal to 1/4. Okay, so this is an interval, so I'm going to use interval notation. So the domain is on the interval 1/4 included, because you're allowed to have 0. 4 times 1/4 equals 1. Take away 1 equals 0. Right? So 1/4 all the way to infinity, and of course you can't ever include infinity. So that's the domain of this function. Let's look at another example. Well, this would be the f of t equals 3t squared over t squared minus 1. All right, so now again, ask yourself if there's ever any time in a fraction that you're not allowed to have any kind of a value show up. And 0 we know is a problem for fractions. But 0 isn't a problem in the numerator. You're always allowed to have 0 in the numerator. You're just not allowed to have 0 in the denominator. So Mayday, we need t squared minus 1 not to equal 0. We need the whole denominator to not equal 0. So let's look for the t values that are excluded from the domain. So t plus 1 times t minus 1 does not equal 0. So t, well, let's just stick with chicken feet because I like them. T does not equal 1 and t does not equal -1. Now in this case I'm not looking at an interval, I'm looking at some specific values. So for me to report the domain, I'm going to have to use set builder notation because it's the only one that lets me choose specific values without having to include the values between those specific values. So the domain is all the elements of t such that t does not equal -1 and t does not equal 1, and t is an element of, now what are we looking at here? Are we talking about the real numbers? Are we talking about the integers? What are we talking about? Well, we know that rational functions, the parent rational looks like this, which means that though we have restricted values, and we're okay with that, we're really talking about all the numbers on the real plane. So t is an element of the real number system. So let's wrap up our review and exploration of functions by talking about piecewise functions. Okay, so a piecewise function is a function that is exactly what it sounds like. It takes a piece of one function and it connects it to a piece of another function and it connects it to a piece of another function. But it has to connect in such a way that the outcome is a function, which means that parts of the pieces have to be erased and not used. So let's look at kind of a general case. I'll just sketch it out as we go. So let's say that we have a function, and this is the shape of the function. It's a straight line all the way from negative infinity, excuse me, I didn't mean straight, it's a horizontal line, all the way from negative infinity to negative 2, and its value is 3. Okay, then from negative 2 to 2, it takes on the shape of a parabola. So let's say the parabola, the part of the parabola it takes on is here. So the parabola actually exists everywhere, right? This is what a parabola would do, right? But we can't include this part of the parabola because if we did, the combined function wouldn't be a function here. It wouldn't pass the vertical line test at that point because this x value would point to the value on the horizontal line and whatever the value on the parabola is. So it's very important that a piecewise function not break the function rule of the vertical line test. So these parts of the parabola then get disappeared and not included. And I'm going to put a dot here to show that it's continuous there. And then say the next function after that was from 2 until infinity was some form of absolute value, right? So let's say it's, well, let's just say it's this. Okay, so some form of absolute value, meaning that the absolute value function would continue right down here, but we're not going to use the part on the interval from negative infinity to 2. We're only going to pick up the absolute value function at 2. So let's put this together as an actual function. Right, so piecewise functions look like this. The f of x equals, and we use a bracket to contain all the parts, it equals, well, the horizontal line has a value of y equals 3, and we're only going to use the part where x is less than or equal to in negative infinity. Yeah, that's correct. Seemed backwards, but it's correct. Then, on the interval from negative 2 to 2, which would be writing negative 2 is strictly less than, because it can't be equal in both places. Strictly, oh, that's where I made my mistake. X has to be less than negative 2. There we go. That looks right now. And then on the parabola interval, it can't be equal here because then you would have you'd have x equaling two different things at negative 2, and so less than 2, right? And so the function there is y equals x squared. And then the last part, we decided that y equals the absolute value of x on the interval where x values are greater than or equal to 2, right? Okay. So let's put this together in well, we're not going to put it together in set builder notation. We're going to evaluate it. So in a function like this, if I want to know what is the f of negative 3, for example, I wouldn't plug negative 3 into each of these functions because this function is only defined for negative 3 when the function is y equals 3. So the function at negative 3 is 3. Right? So the value of the function at, let's say, negative 1, well, the interval that includes negative 1 is here, and so the function that we want to use is x squared. So negative 1 squared, which equals 1. So the value at negative 1 is 1. and then the value at, let's say, positive 3. Well, the positive 3 is on this interval, so this is the function we want to use. So that's the absolute value of 3, which equals 3. So that would be a piecewise function.